The first speaker today is Parul Sohal, and she's a PhD student at Boston University and also an intern at Red Hat. She writes that her work focuses on providing isolation and performance guarantees to applications which are running together on the same system. And the way that that's done is by partitioning off and managing the memory bandwidth allocated to each of those applications. This opens many doors to provide better guarantees for the 99% tail latency in cloud computing and indeed other scenarios. So I'm really happy to introduce Parul's first talk.
Hello, guys. I'm Parul, as Richard mentioned, and I'll just start with my talk. My talk is mostly going to focus on how I can decrease noise when multiple applications are running together and sharing memory at different hierarchies, and the whole noisy neighbor problem. So this should be common knowledge for most present here, but I will quickly recap it. Most modern architectures that sustain heavy cloud workloads have many cores running in parallel. Hence, there is an inherent sharing of resources at the different levels of the memory hierarchy. With sharing comes a lack of isolation. There are two types of isolation: spatial or space-based, and temporal or time-based. A lot of thought has been given to spatial isolation. Manufacturers have been aware of this problem for a while now. Hence, there is a separation between applications run by different users, between the users and the OS, and even between operating systems via virtual machines. But what about time-based isolation? There are three main reasons for time-based interference. First, contention over shared cache, memory bandwidth being the bottleneck, or at the level of the memory controller, because the DRAM can only perform so fast. With keeping these three things in mind, what might affect you depends completely on the workload. In the experiments discussed in this presentation, we are mostly focused on temporal isolation. So before I go into a little more details, I just want to set the stage by discussing two synthetic benchmarks that we use for most of our experiments. First was a Dram Bomb. What it does, it's a DRAM intensive workload. It either performs reads or writes on a 1.5 gigabyte buffer. And to have low cache locality, each consecutive command was 64 bytes or a cache line apart. And the second we use for some of our experiment is a Llc bomb. We decided on the size for 2 MB because it was bigger than the L2 cache partition. But it would still fit in the cache allocated to itself, which we did by using Intel cache allocation technology. So these are the two synthetic benchmarks that have two different goals, and we use them in a lot of our experiments. So let's see how bad is performance in the worst case scenario due to contention on main memory. So on the x-axis, we have number of other cores that are doing a memory intensive benchmark at the same time as the core under analysis. So the 4 on the axis can be interpreted as 4 other cores are competing for shared main memory. And on the y-axis on the left, you can see it's the bandwidth that one of the core under analysis achieves or reports back. As more and more cores want main memory, the main core under analysis sees an almost 50% drop in its performance. As we know, when there are no other cores active, the core under analysis, you can see, is obtaining around 5 gigabytes per second. But when 18 other cores are active, it drops to 2.5 gigabytes per second. Another thing that we repeated is we repeated the same experiment with the Llc intensive memory bomb. And what we found, and the result was very surprising. What we can see is that, and now the x-axis is common, but the y-axis is on the right. And when there's only one core active, it can extract up to 15 gigabytes per second of memory. But when there are 18 other cores also competing for Llc bandwidth, then the bandwidth achieved drops to 7 gigabytes per second, which is almost as close to having to go to main memory. And this result was very surprising because with cache partitioning, the data is already allocated in the cache, and it should not have to act like it was going to the main memory. So this was a very surprising result. So having experimentally known where the bottlenecks are, the goal of this project was to manage two types of contention. One is the DRAM contention, and the other is the LLC contention. For managing DRAM contention, what we use is a software-based mechanism called Memguard, and I can share links and stuff after the presentation to direct you guys to the paper about it. But in short, it's like a budget-based recollection technique. It looks at performance counters, particularly the cache misses. And once a budget or the number of cache misses exceeds a certain amount, then that core is interrupt is triggered, and that core is stopped for the rest of the given period. To manage LLC contention, we used Intel's MBA. And due to the limited time I have, I will skip over why we did this for LLC management and not DRAM management, but a little overview of how it is implemented. The version of MBA used on the Skylake processor is a programmable rate controller between the per core L2 cache and the interconnect between the core and the other parts of the processor. And based on the setting of the MBA, a delay value is added to that particular request. And we believe this is done here between L2 and L3 because of the architecture of the processor. The CPU cores, the memory controllers, the PCI lanes are all connected in a mesh. Hence, except for the memory controllers themselves, there is no component which has access to the information needed to enforce per core bandwidth limits. Furthermore, even memory bandwidth as a whole is supposed to be controlled. Not even the controller has this information, because both the controllers need to share that information. So to provide direct control over per bandwidth, there is a need for some sort of like global state or some global information transfer. This is a very complex feature to implement in hardware. So the current implementation of MBA on the on-core part makes sense. And the fact that it is even adding delay to L3 requests, we can use it to manage LLC contention. So I just want to show how MBA worked in practice. And on the x-axis, we still have the number of other cores active. So they go up from 0 to 19 because there were 20 cores on one socket. And on the y-axis, we still have the bandwidth in megabytes per second. So, and you can see that I have TLH, TL1, and these mean throttling levels. Throttling level 8 means that none of the cores are like regulated or throttled, and they're working at like full blast without any memory regulation. And throttling level 1 is the means that it is being maximum regulated, or if you can think of the maximum amount of delay is being added to each request. And you can see for different levels of throttling, you can have different number of cores active with no decline in the bandwidth received by either of them. So for each level, there is a you can see clearly number of cores a throttling level can sustain before it sees contention. For example, if you look at throttling level 4, you can scale up to 8 other cores before seeing a decline in the bandwidth observed by one core under analysis. And at the max throttling, which is throttling level 1 with the max delay, you can almost scale up to 16 or 17 cores, which is like almost the entire socket, and there is no contention or no performance degradation for one of the cores. And that's why we could use this as managing LLC contention. Knowing all this, we need a model to control all these two different parameters. So we start by defining a couple of terms and constraints. So the first thing that we decided to define was a sustainable DRAM bandwidth and a sustainable LLC bandwidth. And let me explain what I mean by that. each hardware that you ever get has like all these numbers that is associated that, oh, the DRAM can work at this capacity, but which is the theoretical value is not always the same as what the system can actually sustain when multiple applications are running. So what I mean by sustainable DRAM bandwidth and sustainable LLC bandwidth is basically is the bandwidth that when multiple cores can be making transactions to the DRAM without any one of them realizing that there is another application running on the system or seeing any kind of contention. And the way we measured these values was we looked at the graph of the contention and we observed the first dip in the performance of the core under analysis. The bandwidth that the core received was the sustainable bandwidth for that particular core. And then we multiplied it with the number of cores active, and that gave us the sustainable bandwidth of the entire system. For example, for a sustainable LLC bandwidth, there were 2 interfering cores. We saw the first dip. And at that particular instant, that one core was reporting around 11.4 megabytes per second. So with 2 other cores and the core that is under analysis, there were 3 total cores. And if you multiply 11.4 times 3, that is the sustainable LLC bandwidth for this particular hardware. There were other terms that we also had to define, and they were the characteristic DRAM bandwidth, the characteristic LLC bandwidth, the quota, and the quota LLC. We need basically what is the characteristic DRAM or LLC bandwidth is basically when a task is running, how much bandwidth does that task need either for DRAM or LLC, that when from its perspective, it looks like it's the only application running. And this is what we call the characteristic bandwidth. How we calculate this is pretty straightforward. We ran the application we wanted to find the characteristic bandwidth of from lower to higher bandwidth settings, either of Memguard or MBA. And when the execution time with all these settings or the quota is within the threshold to the execution time when there is no regulation, we define that as the characteristic. So let me show you how, before I move on, all these sustainable characteristic quotas, etc., were already in megabytes per second. So we had a unit that we could talk in with. But the MBA, as mentioned earlier, was rather than being in a megabytes per second, it was in throttling level. So it went from throttling level 8 to throttling level 1, and it added a delay to your request, and we weren't sure how much these delay values were, and as it was not mentioned in the documentation. So we needed a mechanism to be able to convert these MBA values into bandwidth. So what we did was we took our LLC intensive memory bomb and we ran it with all the different settings of MBA. We call them throttling levels, but in the system itself, they were called 10, 20, 30, and so on and so forth. And we ran our LLC intensive memory bomb multiple times when there was nothing else running on the system. And we noted what the bandwidth it reported. To make our lives easier, what it did was every time we ran it, it reported a very consistent bandwidth. So that is how we changed our throttling levels into actual megabytes per second bandwidth values. And then a couple of constraints which are very intuitive as well. So if we have some quotas assigned to these Memguard or MBA quotas or megabytes per second assigned to these primary or secondary workloads, then the sum of these quotas should always be below the sustainable quota for either DRAM and LLC, which makes sense because you never want to push the system beyond the saturation level or the sustainable level, because then you're definitely going to see contention and a lack of isolation and these things follow each other, and you're going to see your execution time expanding exponentially. So that was the first constraint we defined. The other constraint that we defined is for the primary workloads whose performance we really care about, that then the setting or the quota that we assigned either to Memguard or MBA it should be more than the characteristic or the bandwidth that that application requires, which also intuitively makes sense. So to conclude all this work, I just want to show one real life work application and the results based on that. So we took spectral clustering, which is a very common machine learning benchmark. And then what we decided to do, as I mentioned earlier, we started from really low values of Memguard, and we kept it going further and further and further until the execution time flattened. And why this is so, because like now, even if we keep giving it more and more bandwidth, the application does not need more than this. So then even if we keep giving it more bandwidth, the execution time is not going to decrease any further. And this is what we decided was the characteristic or the quota for this primary workload for the DRAM. We did the same thing for the LLC bandwidth. We did all the different throttling levels of MBA and figured out when the execution time did not improve anymore. And that was the throttling level for that. So this first bar graph that you see is if we run the application with these particular settings of Memguard and MBA. And what we did, we also compared this to the solo run when it was not being regulated, and they were very close to each other. And for more details about the numbers, I can look at the paper or talk after the presentation. Then what we decided to do was with all the other cores that were on the socket, on 8 of the cores, we ran the DRAM intensive memory bomb, and on 8, we ran the LLC intensive memory bomb, just to act like as secondary workloads or interference workloads. And as you can see that when the 9 other cores are working, the execution time expands by 3 or 4 folds. And just to make sure that only LLC interference was not the only problem, we only ran DRAM interference. And you can see that when there's only DRAM interference, also the running time is higher. And even when we just have LLC interference, the execution time is much higher. Then what we did was, because we always had, we knew how much megabytes per second was being used by our spectral clustering real life workload. And we knew what was the sustainable DRAM and LLC bandwidth. We knew how much bandwidth was left in the system. We took that extra bandwidth and divided it amongst the 8 other cores and regulated all the interference for both DRAM and LLC simultaneously. And what we found were great results that now the application, when the interference is actually being regulated and controlled, and we are not going beyond the saturation point or the sustainable point of the bandwidth, the execution time of the application is very close to as if it was running solo on the system. And this is not the case for just this particular application. We ran the same experiments on a bunch of other realistic benchmarks as well. So I will move on to the next work now. We did a similar work on an embedded system. Instead of Intel RDD, we have a traffic shaping mechanism to control memory requests to main memory in this particular hardware. Also, rather than controlling bandwidth between cores, this hardware does it between masters. Like what I mean by masters is it controls memory bandwidth between, like, let's say different sockets, IO subshells, accelerators, GPUs, etc. Hence, similar to the work I just presented, we had 2 different techniques for regulation. The QoS provided by the hardware and the Memguard to control bandwidth between cores on the same socket, because there is no way to differentiate between traffic coming from the same socket between the CPUs. So we still had to use Memguard. And in this diagram, you can see that Memguard is managing traffic from CPU 1 and CPU 2. Also, another important thing that we had on this hardware was we had an extremely fine-grained profiler. Excuse me. We had an extremely fine-grained profiler, which was also transparent, as it did not affect the traffic from the applications because it had access to its own DDR controller. Like it had, there was no way that the profilers like tracking and recording and all the data saving would affect the application in any way. This helped us better track the memory requirements of the applications and how they could change under different QoS or Memguard settings. And one more thing that we had to do as previously, a key element for providing isolation guarantees is to have the system work below the saturation or the sustainable point. So before we understand what the sustainable point is or saturation point for every hardware, we have to run a bunch of experiments. So that is what we did here. We ran experiments with both Memguard and QoS to understand how reads and write going to main memory affect the utilization of the DDR. So when we set Memguard to around 500 megabytes per second, and our synthetic, as you can see, because this is a smaller system, the bandwidths are much lower. So like the peak was around 1 gigabyte per second. So when we set it around 500 megabytes per second, and we did reads and writes, we wanted to make sure that we were always taking account of the maximum utilization. So as you can see, the writes actually do much more, use the TDR much more higher than when we're just doing reads. So to keep everything consistent, we are always looking at the utilization from reads and writes. We also ran QoS with different settings to see how utilization would be affected by this. And hence, experimentally, we developed a linear model to describe the setting for either QoS or Memguard and its corresponding TDR utilization. And the sum of the two define the total utilization. And I don't want to, because of the time, I don't want to spend too much time on going on the results for this. But what we saw was how if we could basically look at all the different QoS level and Memguard budget levels and provide great predictions of how the execution runtime would change when we had applications not only using CPU, but also accelerators. So just to summarize the result from these two different works, first of all, it's not only in cloud computing, but like even in real-time systems and HPC, it's become really important to try to isolate applications. And one key aspect of doing that is to manage access to the DRAM or like memory management at the DRAM level. So first of all, we need better ways that are in hardware to do it per core bandwidth. And we will be running experiments with the new Intel MBA to see how this will change. And we're really excited about that. Also, now with all the other peripheral devices that have access to like main memory, we also need methods to control main memory transactions from them. It's extremely important that we have a fine-grained and transparent profiling method, which will give us better insight into applications. And lastly, by only making sure that the entire system is always below the sustainable bandwidth, we can make a lot more guarantees about how these applications will run with other applications on the same system. So not to spend too much time on this, but the next stages of the work are also to do that with the new Intel hardware, but also to have a more like refined profiling mechanisms which save the state of where the application was running, how much bandwidth it was occupying or cache. And even when we're profiling the applications, have a more sophisticated way to define how the application is changing in stages, because like memory bandwidth is not constant over the entire execution period, but changes from time to time. And right now, everything is done manually, and we're controlling these policies and like these knobs by manually, but there should be a more automatic mechanism to do this. And I guess that concludes my presentation. Thank you.